what kind of application areas they can be used, and also why do we need unikernel. Okay, so to start with, let's actually start with the definition of what unikernel is. So there's a website unikernel.org. You can have a lot of information about unikernels. But essentially what unikernels are single image operating system. So typically you have a virtual machine, you have layers and layers on top of it, you have a application stack, maybe Docker and so on. What unikernel essentially is that it fuses everything into one image. So there's no distinction between an application, a virtual machine, or anything in between. And I'll have some diagrams to actually include what these layers are and how they're included. Yeah. Oops, sorry. Okay. So let's actually look at the picture today. Right. You have an application. It runs an operating system. Right. Operating systems has usually a lot of lines of code. I don't know. I think Windows is not there, but Windows is actually quite big. Linux, OS, and then you have whole sorts of utilities. So this picture somewhat resembles an iceberg, right? What you care about or what you see is just the tip. There's a really big, bulky stuff that is beneath that you actually don't care about. And as a result, you have a lot of stuff present in your production system that is running that was not part of your application, and often you don't actually need, or not all of it, right? You might need some of it. And the problem here is that software is inherently a very complex thing, right? In software, you have different moving parts, right? You have several processes, threads running, and different moving parts. What it does is it increases the possibility of failures because there is many millions of combinations of things that could potentially go wrong. You also have like millions and millions of lines of code. So millions and millions lines of code means your application would take time to boot up, to run. And lots of code also means that there are lots of vulnerabilities, right? So every now and then you hear stories about XYZ hacked this website, all sorts of buffer overflow attacks and so on. And the problem is all these attacks that are happening, very many of them are happening at the part of the code that you actually don't use. And you just have it for the sake of having it, and your application suffers because of it. It doesn't really get any benefit about it. So all this complexity is kind of unnecessary, right? And the reason why we have these complexity is because an operating system or a Docker, even probably less true for Docker, but still the same thing, they are general purpose systems, right? They don't have any particular use case in mind, and they don't have any particular user and so on, and they don't even have any estimates on the size that you use. So they are trying to create this one solution that works for everybody. And what happens is it kind of works for everybody, but it doesn't work perfectly for anybody because it's like a jack of all trade, master of none kind of situation, right? So you have all this complexity, and with an operating system, you have a lot of different configuration points, right? You have to configure this, you have to configure that, which often you don't use. And if you look at the trends that are happening, people are moving towards microservices, and people are moving more towards, in an abstract way, what we are moving from a monolithic to a world of microservices where you have more granularity and assembly of smaller systems working together than having one big large ball of mud, as I like to call it. And these microservices, they follow the single responsibility principle, which is rather than having a jack of all trade system, focus on one thing and do that one thing really, really well. So the current scenario that we have is kind of an anti-pattern in the modern world. Most apps are single purpose. Most microservices want to have one or two endpoints. Yet we have to inherit this huge big bulk of code that we don't use. So the question is there a way to reduce the complexity? Can we do that? Turns out there are ways of doing it. We'll cover that. Another problem that we have is lack of portability. That portability probably is not big of a problem when you're running on some sort of managed environment, for example, Java virtual machine. It's not a big problem. It is a problem to some extent. But if you're using like a low-level native app, like something like a C++ app, you're using operating system libraries. And as much as you have standards, not everybody follows the standards 100%. So you end up in a situation where your code is semi-portable, right, across different platforms, across different devices, and this is often not a good scenario, because in the modern world, what we have is we have a set of a lot of these devices that work together rather than having like one common pattern. So it becomes difficult to reuse the code, and that's one of the things that we need to worry about. Can we enhance the portability? So for us to have this problem solved, what we need to do is we need to have a solution that somehow, focuses on the problem at hand and distangles you from the underlying system, operating system, or whatever platform you're using, right? You want to focus on your code and not worry as much as possible about the rest of it. You also want to do something like, if I don't need 50 services, I shouldn't have them, right? My application is a single process application in a microservice, right? I need easy scalability, but let's say I don't want too much threading. I don't want a file system. I'm not storing anything. It's a stateless application. I have a DB connected, right? But I still have a file system. So if you have a solution that only takes all the components of the operating system that you actually need, you solve a lot of security problems and a lot of portability problems that you otherwise inherit. And finally, you would need something like, from a single platform, I should inherit multiple platforms, right? So can we have such a practical solution? Well, we kind of have it. And that solution is called as containers, right? So what is a container? A container is essentially a stripped down VM. So you don't inherit the entire VM. You have like a subset of bare essentials. You build layers and layers of your application, and essentially you have a Docker, and any platform where containers are supported, you can package your application, you can run it on your local system. Hey, it works, then I can take this container as a whole and deploy it on my production environment. It works. You have different tools like Kubernetes, Mesosphere, you're running containers at scale. Things fail at scale, so you need a way to handle resiliency, all those things, good. And you can deploy it to multiple platforms. So far, so good, except the problem is, this is not a perfect solution. It's better than what we have in the VM world, but not a perfect solution. Why? Because containers don't really eliminate the libraries that you don't use. They just reduce the amount of it, right? So container is basically a mini VM. That's what it is. All the services of VM, you still have those services in a container. Not that you don't have it. You may not have as much of them. You have less code, sure, but containers are inherently, there are issues with containers, especially on the network. If you have one VM and you're running a lot of containers, you're likely to have problems. So containers are a solution. It's a step in the right direction, but it's not the perfect, or it's not the ideal solution that we are looking for. Obviously, there is no such thing as an ideal in the world, but what we want to do is we still want to go as close as possible, where we reduce the amount of inherited code that we have and focus more on the application. And that solution comes with Unikernels. So what is a Unikernel, right? Essentially, what you have is your whole operating system has certain set of components. A Unikernel, what it does is it takes your application code and it takes all the components of the operating system that you actually need and ignore the rest that you don't need, which is going to be 90% of the case, and package them together. Sorry about that. I don't know why is this happening. Okay, good. Something happening with the connection. Okay, I'll just keep talking until, yeah. So what a Unikernel actually does is takes this library components and fuses them together as an application, right? So when you're building your application at build time, it takes those components. We'll see some example, and it only uses the libraries that you actually require. And a Unikernel really is a single process system, right? You don't have a lot of processes, let alone threads and so on. And what it does is, let's say that now I want to port my application in some other platform, right? I still have the uniform interface where I'm calling the OS libraries. So my application is ported, let's say, on JVM. Now I swap it out and I want to put it on a hypervisor running on a Zen virtualization server. So a unikernel will target multiple runtimes. So I would build that application for the second platform that I have. It takes the same components that run, it takes the equivalent components, right, that have the same interface, and it packages it. It runs on another platform. So think of it something like, let's say you have something like a Docker, but is not one such Docker, but there's a Docker for different kind of environments. So you can package it in a similar way and generates a different container for each one of the target platforms that you can deploy. But you don't really have to change your application for it. Your application, the interface for those components are still the same. So your application remains unchanged. You just have to recompile your application for your different platform and you're done. So this is traditional application stack, right? You have a kernel space and then you have a user space, and your operating system, process management network, all those things, they use the kernel space, and then your application library routines uses the user space. One of the performance problems that you have with this is that you have to switch between kernel space and user space rapidly when you're running. What Unikernel does, it fuses them together. So what you have is there. And by the way, this networking and that networking is not exactly the same. For example, you may not use all components of networking. So that component would only have the stuff that your application actually needs. And notice that there is no process management because you don't have processes in Unikernel. And let's say if you don't use file system, you won't have file system in your application. So it's like on demand basis. So this is how Unikernel application stack would actually look like. Okay. So let's actually look at the evolution of evolution in the, I'm so sorry. I think the connection is weak. Can somebody have a look at it? What's happening here? Yeah, it's just going blank. Okay, now it's working. Yeah, but I think there's a loose connection there. Okay, sorry for the interruption. So I was at evolution. See, it again goes back. It's, I think you can stand here, and if something goes bad, you can fix it. So just be here. That's yeah. My apologies for this, but anyway, let's actually look at evolution, right? So you have the hypervisor, and then you have big, large components of OS, and then your application. And when you look at how the space is moving, what you see is that the app component increases more and more, and the OS component shrinks. So what you have in Unikernel is nothing but the next step of evolution beyond containers. That's what Unikernels are. But there's a general trend that we should focus more on the stuff that we actually need and less on stuff that is just an overhead that we may not even use. So what are the characteristics of Unikernel, right? What makes Unikernel so unique? So I already kind of discussed that. Unikernels are often high performance. And the reason why there's high performance is because there is less code, right? There's less overhead, and there is there's no switching between user kernel modes. So they actually operate very fast. They're obviously a lot smaller because you don't really have a large overhead of OS code. In fact, there have been cases where unikernels basically just going KBs. If you tell somebody, KBs, they'll be like, are you kidding me? But typically for microservices, right, you're only handling one or two endpoints. You don't really need a lot of code for that. So unikernels tend to be very, very small. And another characteristic is faster boot times. Because you have less code and your code component, your hypervisor component, your operating system varies thing, you don't really need a lot of time to boot. And this actually has a very interesting property, and I'll cover that in details in the later slide. But you could have something like an on-demand provision. Sorry. security often, okay, let me move to slide back. Yeah, that actually is a problem. Generally, because everything has a root privilege, you don't really have a concept of security. Well, I mean, you are trusting people who are writing the code to write code. You have methods to test code and all those things, right? You have producing logs and so on. So you have a mechanism to audit, and you have to trust your development system. I mean, there is no built-in security. You could potentially add a layer. Nothing stops you from doing that. But there is no inherent security mechanism. And it's a little bit of a design philosophy also, because the very fundamental principle of a unikernel is have what you only need, don't have what you don't need. So if you need security, you can add a layer yourself, but unikernel will not enforce a security for you because it wants to give you the freedom of not having it, right? That's a kind of a trade-off. I mean, it's the same thing as, and this is another thing that I've covered later on, is like, if you have a lot of utilities of your OS that you actually need, then unikernel is not the best way, because you don't have that equivalent in a unikernel, right? The very premise of unikernel is be lean. Just have what you need and put things as you go along. Did that answer your question? Yeah, sure. Okay. So I was talking about the application of faster boot time. When you have microservices, you want to scale up, you actually can scale up on demand. So if you have load, you have an auto balance that scales up, because provisioning a unikernel and booting it so fast, you literally can do it on demand. There's actually a slide, there's a project about it, Jitsu. I'll have the details in that slide, which is what it does. It just, every time you get a request, it provisions a new unikernel as your load expands, just on demand. And it works because it's just few milliseconds. You won't even notice it. Okay. So in the embedded system world, what you have is, when I was a kid, I used to play with, not so much of a kid, but in graduate school, I used to play with those microprocessor kits, right? You have the 8088 assembly language, and you have a development environment on a DOS PC. You write that code, you have an emulator that tests it, everything. And finally, when you deploy it in production environment, which is a microprocessor kit in this case, like an embedded environment, right? It produces that binary that you load it on your microprocessor. And that's a single image binary. So in a way, unikernel applies the same philosophy to the cloud. That when you develop it, you have emulators, you have testing stack and everything, and you test everything's okay. And when you talk about deploying, it just fuses everything as one binary image and just deploys it on your hypervisor. And the problem with that approach, which is even an approach with an embedded system, is you have no visibility of what is happening in your actual production environment. So during your development, testing, you have all the tracing, everything, you're using emulator. But when you actually put it on your device, that's the end. So that's kind of a drawback, and how you actually, usually they do it in embedded systems, and you have to use the same approaches. During the development, you could have logging, right? So you take that issue, and you replicate that issue in your debug environment and figure out what's happening. Some people consider it as a drawback to unikernel. I personally don't think it as a drawback, because I've never come across someone who does live debugging in production. What you're really doing is you're replicating that in a debug environment. Nothing stops you from replicating that in the debug environment anyway, right? So for someone, and I don't know of anyone like that who does live debugging in production, that would be an issue, but not for most of us. Use case scenario, okay? So microservices is like really popular these days. Every talk on software architecture talks about microservices, and unikernels are quite a good platform, quite a good way to approach to implement microservices, because they are small, independent, single responsibility principle, and they have low boot times. I already covered that, right? That means rapid scaling, because you need that elasticity when you operate at scale. Another potential application is immutable infrastructure. So you reduce your dependency on external components. How? Just take everything and prepare it as one image. So statically link the data. So these are different use case scenarios. These are just typical use case scenarios, right? There's obviously very many of them. So let's actually move on to the development of it. So how this is how a development stack would look like. Okay. So during a development, you have your standard operating system and you have a development runtime, right? Typically, how it works in embedded, right? You have an emulator. Think of it as an emulator. So your application compiles. You don't actually need the kernel routines because your standard operating system is providing you that during the development phase. Then, once I have the development done, I move to the testing. So testing would have all that. Testing still will take all those kernels and file system because you want to know how your application will behave in the production environment. So you take into effect, but you're still running under the standard operating system. And finally, once your testing is done, you actually move to the production. So production takes everything and then puts it on the hypervisor. And this is where you lose all the visibility of your system. Another thing I should actually caution about Unikernel is that because there is no difference between an operating system and an application, let's say you allocate 4 GB of RAM to an image, right? On your system, it will show that you have 4 GB. Finish. You're consuming all 4 GB, even if you don't actually use it. Whereas I think in Dockers, you actually have the ability to take some GB from one container and put it in another. You would not have that you would not have that facility in unikernels because the fundamental fact is a unikernel does not differentiate between what is an operating system and what is an application. They're both the same. And what tends to often happen is that you don't want your system to crash during production from running out of memory. So as a result, you tend to overestimate the amount of, because you want to play it safe, you tend to overestimate the amount of memory that you actually need and provision it accordingly. All right, so let's actually go to the benefits of using Unikernel. Well, first and foremost, you have smaller image. So you have smaller image means you have either you can use a cheaper VM or you can have high multi-tenancy, right? So you can have several applications packed in one VM. You have reduced memory print and you have reduced computational burden. So you don't actually need that much of computation power to power a unikernel application as much as you would need in a traditional, let's say, VM Docker based application. Another advantage, boot times. You're talking about milliseconds. So reduced, sorry. Okay, sorry. Text is wrong. Faster boot times, right? You have really fast boot times because you're talking about milliseconds. You have less amount of code. Better security. You have less amount of code means you are giving basically an attacker less attack surface. Because an attacker would exploit known vulnerabilities of OS, and chances are you actually don't use those components in the first place, so attacker can do anything. You also don't have a command line shell. So you can't have like a root privilege and run root commands. You just don't have it. So reduced attack surface essentially gives you a lot better security properties in kernel. Okay. Why not use Unikernel? So far, so good. We are talking about all the benefits. Obviously, this is not a perfect solution, and there are drawbacks. To start with, you're working on the premise that I don't use a lot of components of operating. I don't need all the components of operating system. But what if you need them, right? So this is Unikernel is like an on-demand, right? I don't need file system. I don't have file system. But what if you need it? There are times where you need a lot of utilities, and obviously those are the times you don't want unikernels because they would not have all those. You have to implement it yourself. It's too much of a burden. So there's a lot of software for Linux that is not present in unikernels. And one of the drawbacks generally with unikernel is that it's relatively a new technology, right? And with any new technology, there's a lack of tooling. There's a lack of knowledge. There's just not good enough ecosystem. Hopefully this is something that we would fix as time passes by, but that's the state of affairs right now. Unikernels are still gaining popularity. I think with the switch to microservices, I would say that adoption of unikernel is going to be much more than um, as opposed to now. But it's still, it's a while before we see unikernels entering a mainstream technology. Okay, so we have a lot of implementation. I just have some of them, right? But if you go to this website, you have a lot of them. Um, one of the things with unikernels is because the operating system and application is fused together, you have a limit on a certain kind of programming languages because you don't really have a general purpose system that a VM has. So for example, Mirage OS, you will have to have your application in a language called OCaml. For those of you who are not familiar, it's a functional programming language from the ML family that was in 1975. They had this language called ML used for natural language processing, theorem proving, and so on. So Mirage OS is there. You have Click OS. It boots under 30 milliseconds, very tiny. You have Haskell's VM HA11. This is actually made by a famous company. It's called Galou. It's actually a French company. They write it as Galois, pronounces as Galois. This requires you to have Haskell. You also have some kind of unique kernels that basically emulate something like a Tomcat server, right? So any application that is running on Tomcat server, you could potentially have it in unikernels and put it on this. I forgot the name. I think it's OSV. OSV is an OSV is there. Yeah, this one. This actually I think emulates the Tomcat server. Okay. So one of the popular virtualization server for unikernels is Zen Virtualization Server. And what Zen Virtualization Server is it's a microkernel design, right? So it doesn't have that monolithic. It uses para virtualization. What is para virtualization? Let's say that you're running a network, right? Your data comes in, your data is unpacked, and then your application, because the application does not know whether, let's say you're running on a host VM, right? And you have several VMs running on a hypervisor. Your application does not actually know whether you're running on a hypervisor or on a native VM, right? It's transparent to that. So you have a data coming from the network, you actually unpack the data, and then you have to repack the data and then send it to the application, which will unpack it again. So para virtualization is sort of essentially a modified image where it makes a certain assumption and it's aware of the fact that I'm actually running in a hypervisor or in a virtual environment and not in native. So it expects a uniform interface, and in that interface, it actually can do a lot. It doesn't have to do a lot of unnecessary work that a traditional VM on a hypervisor would have to do. So what it gives you is the benefit of having high performance. Zen is a very high performance hypervisor, and it also has a live migration. What is a live migration? The term live migration actually is a little bit misleading. It's the right term, I think, would be semi-live migration. But what live migration is, that you can move your image while it's being run from one physical host to another physical host with almost no interruption. And I'm using the word almost because there is tiny impression. That's why I'm calling the semi-live migration. But you could do that. Whereas you can't do something on like that on a Docker, right? You have to stop, redeploy in a physical host. And that's important, let's say, in an application areas where you have to move an application running from one data center to another data center because maybe your users come from another part of the world. Let's say I have an application running in a US data center and suddenly I have a surge of application coming, a surge of requests coming from China, and I think it's actually better lower latency for me to move this application from my US data center to Chinese data center. You can do that without interruption. That's what Zen allows you to do. A lot of unikernel projects actually target the Zen virtualization server, including Mirage OS. And talking about Mirage OS, let's actually introduce Mirage OS. So Mirage tool basically builds these unikernels for various backends. Now what you see here, I don't know if it's visible. I think it is. Yeah, so you have different backends, x86 hardware, the browser, and Google Java, which can run on Google App Engine. And what it does is that it has these components for all of these backends. So it takes your application, and you have to write your application in OCaml to be used for Mirage OS. and combines it, and you can retarget all the different kind of platforms that Mirage OS supports. I think the Mirage OS 3 has some additional. This is up till version 3. Version 3 supports some additional platforms that I have not included here. Okay, so we talked about on-demand application. Well, there's a project called Jitsu. That's the source, and what it does is just-in-time summoning of Unikernel. So as I have a request, I can just boot up a Unikernel, process that request, and there are all sorts of different configuration. I can keep it alive, but if I see that the request load is doing and I don't really need that many instances of the kernel, I can shut them down. You could do the same thing in a traditional environment. The problem is that it takes more time. It takes few seconds for you to boot up and shut down. Whereas in Unikernel, because that boot up and shutdown process is really, really fast, you can do it quite nicely. Like you can do it at a rapid pace of scaling, downscaling, and upscaling. So DNS server would start the Unikernels on demand. It's actually been tested on Mirage OS. Mirage OS folks, they actually have this Jitsu project and trumped up Unikernels. Anyway, so I have some resources. For Mirage OS, you have this. For Unikernels, I already showed this website. Actually, wiki page is quite, it describes Unikernel quite well. There are some research papers, there are some articles, and we do have a book from O'Reilly about Unikernels. So that's a good reference. Coming towards the end, the conclusion. So Unikernel is a promising new technology. It's actually the next step of evolution, but again, right now it's kind of immature. I would see the adoption growing more as we move more towards the microservices world. But relatively now, it's in its infancy. It's particularly relevant for cloud and microservices era, as I mentioned. Their secure images support very high multi-tenancy, very fast boot times, on-demand provisioning. You have a lot of open source projects. There are some commercial projects also, but they support a large number of different platforms and runtimes. But yeah, it's still in its infancy, and there's an ecosystem around it is relatively immature. I'm up for questions. I think microservices would have a lot of use cases. I do not know of right now. I'm not aware of any big case study or any particular commercial application that I can point out, because it's again, like I said, it's relatively new. There's open stuff running, but I would say that microservices would be one potential application area that I could completely see. And what makes Unikernels really good for microservices, there are two particular things that stand out. One, or actually three, I would say. One, they are small images, which means high level of multi-tenancy. So that's more cost effectiveness for you, right? In one VM, you can run many instances. B, security, less attack surface. And three, fast scaling. Because you have low boost time, you can create more instances very fast. So microservices is actually something like a really good application area for Uniservices. Microservices obviously have gained a lot of traction. Many organizations have adopted it. Some are still in process. I had a friend in Microsoft. He actually called me last week. Microsoft has now started adopting microservices. Yeah. So those would be the particularly niche areas for Unikernel. Like any application, I'd say that it picks up when you have a certain niche areas where there is a dying need for it. And I see the potential. How far would Unikernel go? Nobody knows the answer. Any other question?
I think what would happen is that the way I see it is that most of the applications right now leave the entire spectrum of OS is because they are there. Someone is doing network, someone is doing some part of the application, doing file application, some part of the application might also be doing image processing. So that's why you need the whole stuff.
Yeah.
But let's say if I have to emulate this in an unikernel environment, I will still have different unikernels using different portions of the OS, and the vulnerability part which you talked about might still be present in one of the other unikernel which is currently deployed in my
Hmm.
entire ecosystem.
Yeah. So I agree with you. Monolithic is obviously an anti-pattern for unikernel. I think in terms of adoption, and this is not related to unikernel. See, the graph is not a linear graph that you grow over time, right? You have some early adopters and they experimented, and everybody says things, and then you have a little bit of disappointment because people start thinking, hey, this is the perfect technology. Unfortunately, there's no such thing as a perfect technology. And finally, you find like one or two niche areas where suddenly it becomes popular. Hey, this is the kind of problem solved, and then everybody starts doing it. So the graph would look, initially the growth is slow, and then there is an inflection point, and then it picks up. uh, Unique kernels have obviously not reached that inflection point, and hopefully they do, but obviously there's no such thing as a guarantee in that aspect. So yes, we are in the infancy, and also for a lot of high adoption, you need a mature tooling. Tooling is often very important. I mean, I've had people using antique systems just because everybody uses Java. Sorry, in my personal opinion, they suck, but hey, it has an excellent ecosystem. There's no doubt about it, right? So the ecosystem actually matters. And it becomes a catch 22 situation, right? People want to adopt because there's a good ecosystem, but there'll be a good ecosystem because there has to be good. Yeah. So once that cycle hits a mature point, you would see the growth. We are not there yet in terms of unikernels. Any other questions? During the build time. During the build time, you can actually, because you import the library. See, think of your traditional operating system, right? You're importing certain headers. So imagine that let me talk a very simple C++ stuff. You're importing stdio or some sort of header, right? Now, if you have a smart compiler that says, okay, you imported stdio, but I know from your code that you actually used the 10 functions out of the 50 functions, right? I would create an stdio for you that only has those 10 functions. And obviously, if those 10 functions call something else, then I would have those dependent functions. But I would not have everything, right? So a Mirage compiler or any Unikernel compiler is smart enough that it knows when you declare that these are the dependencies you actually need. So it has this entire operating system, its library components, and it just pulls those components as and when needed rather than just pulling everything. And that happens during the compile time. So when your image is built, it only has those necessary components. Any other questions? Okay. Thank you.